welcome back to my system design series. In this playlist, we are trying to cover DDIA book of system design. DDIA book is also considered as Bible of system design. So, in previous videos up to lecture number 33, we have tried to complete chapter number 1 to 6, and from lecture number 34, we have started chapter number 7, that is transaction. So, in this lecture number 35, we will cover atomicity and isolation as a single versus multi-object operations. We have already covered atomicity and isolation, but in this lecture, we will go in that. So, atomicity as all or nothing transactions, isolation as no interference between transactions, then single object operations, multi-object transactions, what can go wrong without atomicity or isolation, and handling failures and safe retries. Then asset databases versus best effort systems. So make sure you watch at 1.5x or 2x for better experience. Okay, let's start. In chapter number 7, there are two key transaction concepts. First is atomicity and second is isolation. These properties ensures that the data modifications happens reliably even on the presence of errors or concurrent activity. In simple terms, atomicity means all or nothing. A series of operations either complete entirely or none of them exist. While isolation means no interference. That is, concurrently executing transactions act as they were run one by one. That is, without stepping on each other's toes. So just assume that these are kind of parallel lines. So they won't interfere. In this video, we will understand this concept with real world analogies and simpler diagrams. Okay. Let's move forward. Let's discuss what is atomicity, that is all or nothing transactions. Atomicity is the context of transaction, means that the group of database operations is treated as single single and indivisible unit. Either all the operations in the group will succeed or none are applied. There is no partial completion. Okay, let's understand this by taking an example. Suppose there are two variables A and B. In operation 1, you try to sum them A plus B. And here you will get an answer. Okay, that is a C. Now in operation 2, what you do is the answer which you got in operation 1, then you multiply it with A variable. Then here also you will get the answer D. Okay. In operation number 3, what you do is you multiply this answer with variable B, and here you will get the answer as E. But what if this operation 1 executed, this operation number 2 executed, but this operation number 3 didn't executed? Because of that, this operation 2 and operation 1 will be rolled back. So nothing is happened. You didn't found the value D, you didn't found the value E, and you didn't found the value C. So you will be directly in the step this, that is step 0. Suppose this is step number 1, 2 and 3. But up yahan se you have came to the step 0. So nothing happened. So this guarantees that we never end up with half finished results. So this is the concept of atomicity. Okay, let's consider a real world scenario. For example, there are two people, person A, person B, Alice and Bob. So the first person is having $100 in its account, and Bob have only $0. So suppose they try to do a transaction where Alice gives $50 to Bob. So this particular transaction will have two operations, that is operation 1 plus operation 2. In operation 1, from the Ali's account, $50 will be deducted, and in Bob's account, $50 will be added. Okay. So operation 1 and operation 2 will be successful, then only this transaction will be complete. But now what if in between, like for example, operation 1 completed successfully. But what if while doing or while performing operation 2, this operation 2 faced some issues? some errors, or maybe server broke down. So it won't let this transaction to be as it is. Either it should complete both the operations, or it should roll back the operations which are already completed of this transaction. So here in this example, we have only taken two operations, but there would be multiple operations in real world. So the $50 which was deducted from LI's account will be rolled back. So no deduction is happened. So as it is, LI's will have $100 in its account and Bob will have $0 in its account, which means it preserves the consistency of both the accounts. Without Atomicity, Alice might have lost its $50 without showing those $50 into Bob's account, which is clearly unacceptable outcome in the banking system. Okay, let's move forward. Let's understand how this atomicity is achieved. Databases implement atomicity by the techniques such as write ahead log, journaling for crash recovery. Every change or every transaction is first recorded in a log. Now, this log is a kind of timestamp. It shows that this particular time, this particular operation or transaction or this particular step have been executed. And if a transaction is failed partway due to error, crash, etc., the database will use this log to undo. Suppose these are some of the transactions, it will undo them to restore previous stage. Only when a transaction commits, that is successfully completes all its steps or successfully completes all the operations, then this particular log record will indicate the transaction has been completed, and only then the changes are made durable. This way, if a server crashes or restart, it will discard or roll back any transactions that didn't commit, which ensures that we don't see half updated data, which makes it very useful part of any transaction. Okay, let's move forward. Let's understand what is isolation. That is, transactions don't interfere. Isolation means that suppose there are two transactions which are going on, they don't interfere in each other's way, that is they don't interfere in their intermediate states. Even if the transactions run at suppose the same time, isolation creates the illusion that each transaction, this is transaction 1 and transaction 2, are running alone in the whole database. The end result of all the transactions will be as if they executed one after another. Transaction 1 executed, then transaction 2 executed. It's a kind of illusion which has been created, even though they might have been implemented at the same time. In practice, the perfect isolation, which is also called serializability, is the ideal. This guarantees that the outcome is same as some serial order of transaction. So here understand that full serializable transaction will be very costly. So because of that, many databases uses some weaker isolations, that is isolation levels, for better performance. But here the basic idea is to avoid what? Avoid anomalies. But not anomalies, but concurrent anomalies. Let's understand this by taking an example. Suppose imagine that there is a bank account which is having suppose $100 as of now. And this account is being accessed by two people. Suppose this is person 1, which is Alice, and this is person 2, which is Bob. Now, both of them thought of like eating food and they try to deduct or get this $80 from this bank account. But what if this both the person try to deduct the $80 here, Alice, and $80 by Bob at the same time? They both saw that enough amount is there in the account, but if there is no proper isolation, then how this situation will be handled? But because of proper isolation, this whole situation will be avoided. So, in this situation, proper isolation will make sure that whenever a transaction starts, then at that time, the lock is been applied to this account balance. Lock is been applied to this account balance. So, once this allies have completed its own transaction, this Bob will see that as of now, only $20 are there. And this is the updated balance. So here the end effect is that one withdrawal have happened before starting the second transaction. Now imagine that if there is no isolation level, then this both the transaction will try to deduct $80 from it. They are interfering in each other's transaction, which will cause improper outcome. That is, because of this, money can be lost, there can be duplicate transactions, and if there is a product, it could be sold twice and etc. So you have to make sure there is a proper isolation level. I hope that is clear. But now understand that how this isolation level can be achieved. So to achieve this, database uses locks, latches, or multi-versioning isolation. For example, the database can put a lock, suppose this is a lock, on whole row, or it puts a lock on whole document, while a transaction which is running and it is modifying any row or any document, so that other transactions can wait or use previous committed version of that data. This prevents anyone to see that partial updates or overwriting the same data which transaction 1 is as of now working on it. So, this particular person might be overwriting that data, which is not ideal. Some database uses MVCC, that is multi version concurrency control. That means having the older version of the same data, suppose this would can be data, suppose version 0, this is version 1, this is version 2, it keeps the older version so that if there are any readers, they don't get blocked when someone is trying to update any document. So, as we have already discussed, when you are writing on the data, you are locking that document, right? But this reader can see the previous version of the data. So, here the main goal is that no transaction can see the in progress work of another, but they only see the committed data. Okay. Let's move forward. Let's understand single object operations, which is built in atomicity and isolation. Even when the database operation involves only a single object, for example, one row, one document, one record, or any key value pair, atomicity and isolation will still apply on this and are important. In fact, almost all storage engine provides atomicity and isolation at least at the level of an individual item. Now, what does this mean? That if you update any one record, that update will be all or nothing. And other clients won't be able to see the half done changes on a particular record. Although we have often talked about transactions as grouping the multiple operation, for example, operation 1 plus operation 2, here as an example, but this concept makes sure that even one single object is treated safely. Okay, but you might have a question that why even single object, that is single record, document or key value pair, rights need this isolation or atomicity? Okay, to understand that, consider a large document or single row is been written. If you are writing 20 KB JSON document to a database and a network fails after sending only 10 KB of data. Now pause a minute and think that will this database will save or store this half truncated document? Ideally, no. It should drop the partial write and keep the older document thanks to atomicity. Now, another scenario is what if the power fails when you are overriding an existing value on a disk? Now, think, could we end up with part of old value and part of new value, which is old value and new value mixed together on the disk? Again, no, because of atomicity. Because atomicity guarantees that on recovery, that is when you get the network back, the value could be either in their older version or it could be wholly in the newer version, not a splice of both. That is, it won't be mix up of older values in the half part, this would be older values and this would be newer values. This won't be possible because of the atomicity. Now think of another example or another scenario that if a client is reading a record which is also updating at the same time, will this client will see the partially updated values? Like for example, as of now A's value is 10 and B's value is 20. This B's value is been updated to 30 while executing this particular transaction. So will this guy will see this A equal to 10 and B equal to 30? So no, it must not see the updating value. That is, for example, when any transaction is updating the record, it should not see this particular value until it has been committed. So, as we saw these three scenarios, which guarantees that all the storage engines make single object operations atomic and isolated to prevent any partial updates or store writes in case of failure. Under the hood, the database might use some logs to record the new value before replacing the older value and provide a log on the object which is being updated. The result is like that a single key write behaves much like a tiny transaction. It will either be applied in the full or not at all. And outside observers will see the state either before, that is an older version, or the updated version, but not the middle version. Okay, let's move forward. Let's talk about multi object transactions, that is, grouping multiple writes atomically. Often we need to perform operation that have multiple objects. That means multiple rows, documents, etc. And we are trying to keep them in a sync. That means grouping several read write operation into one logical unit of work so that atomicity and isolation span all those operations together. In other words, the transaction as a whole is all or nothing and hidden from other transactions until it is completed. Okay, let's talk about when we need multi-object transactions. Okay, so let's discuss some common real-world scenarios. So first is maintaining invariants across records. For example, inserting a new row with a foreign key reference. You might need to insert a record in table A and its related record in suppose table B. Both the inserts either should succeed or fail together to avoid a reference to a non-existent record. Also, no other transaction, suppose transaction 2 or 3, should see the record A in table A without the reference of that record in table B. That is isolation. Moving towards the next one, that is denormalized updates. In this, in the document or NoSQL database, you might store redundant data for a fast read. If you want to suppose update a piece of suppose information, that is record A, which is appearing in several documents, you want to update the value of record A in all the documents atomically. Otherwise, one document might be changed while document 2, document 3, document 4 or other documents still have the older data, which causes inconsistency. A multi-document transaction can ensure all copies are updated together. Moving towards the next one, that is maintaining secondary indexes. In this, when you update a data record, its indexes should be also updated. For example, if you change the user's email ID in user table, you might need to update the user's email index table as well. So this multiple writes, that is a user row, and the index entry should be one atomic unit. You would not want the user's email changed, but this email index is still pointing towards the older value of that email. So transactions lets you do the updates, both the updates together. Moving towards the next one, that is complex business actions. In this, consider a shopping cart checkout. Placing an order might involve recording the order, deducting the entry of the particular product record, and logging a payment transaction. All these modifications across different tables or collections ideally occur in a single transaction so that it is impossible for some parts to succeed while others fail. You don't want to charge the customer's card but not create the order, or create an order record without reserving the stock. And grouping all of them in one transaction ensures consistency across various objects. Okay. Without multi-object transaction, it is still possible to implement such logic, but it becomes much more error prone. The application have to check manually all the partial failures and compensate for them. For example, manually undo the steps which you have already followed and ensure no concurrent interference. This is tricky to get right. With transactions, the database take care of atomicity and isolation for it, making the programming much more simpler. Okay, now let's talk about challenges and trade-offs. Many distributed NoSQL data stores historically did not support multi-object transactions, but when before, like long ago, especially when data is partitioned across many nodes. Ensuring atomicity across various network partitions or shards, it is very hard and can reduce performance. But such systems often limit transactions to a single key or document. Here, the benefit is higher scalability and availability. But here, the downside is maintaining consistency falls on the shoulder of developers. Modern databases include some new SQL and distributed SQL databases have worked to offer multi-object transaction, ACID transaction, even across distributed clusters. But there is often a performance cost. It is a classic trade-off. That is stronger guarantees versus throughput and complexity. In summary, if your application needs updating multiple pieces of the data together reliably, an ACID compliant database with multi-object transaction support is extremely valuable. Okay, next we will see what goes wrong when atomicity and isolation guarantees are missing. We have already discussed the dangers of violating isolation and atomicity. Let's just recall. So one of that example is, as we saw here, when Alice and Bob were having some transaction discussion, and Alice was transferring suppose $80 to be that is Bob's account, but because of some issue, the deduction happened from Alice's account, but it just got transferred to the Bob's account. So that is the dangers of violating atomicity. Then the another example which we discussed was this one, where we were transferring this document, that is a 20 KB JSON document, but because of some error or maybe some server crash, only 10 KB was got transferred and remaining 10 was left out. So due to the atomicity, that whole document or partial changes were rolled back. If it didn't roll back, then it might have faced the consequences. Then another example, I guess, which we have discussed is this one. When one person was trying to change the value of B, but this another person was able to see the particular transaction, and it might affect its thoughts and it will affect his own decisions, right? So, due to the isolation, it is causing the consequences. So these are the some of the dangers which we have discussed already, but these are not just the theoretical edge cases. Concurrency bugs and partial updates have led to some serious issues. For example, money lost, duplicated some entries or transactions, corrupted applications data, and the most important, audit failures in financial. A famous example is the Bitcoin exchange that lost track of balances due to the race condition in the database updates, which led to financial losses, forced reconciliation. This is why the database research and engineering put so much emphasis on transactions. In critical systems, you want the safety net of atomicity and isolation to avoid this hard to detect and costly bugs. Okay, let's move forward and let's talk about handling errors and aborted transactions, that is a safe retry. One big advantage of atomic transaction is error handling. If something goes wrong, you can safely abort and retry and remove the partial updates. Since atomicity ensures that a failed transaction has no partial side effects, it is like as if it never ran. An application can attempt the whole attempt from the scratch, hopefully succeeding for the next time. However, in practice, retrying the transactions is not always straightforward. There are some important points to consider. So let's discuss one by one. First one is, did the transaction actually succeed? If the transaction has been successfully committed, but the acknowledge didn't reach to the client due to the network outrage or something, but the client thinks it is failed. If it blindly retries, it will perform the operations again, potentially duplicating them. For example, suppose you submit a payment transaction and it got failed, but the connection fails before you get the confirmation. You retry the transaction, but now the recipient will get the paid twice unless there is some duplicate check. The system or application needs some way to check this particular duplication. They can use unique transaction IDs or deduplicate this particular whole transaction. Second is what caused the error. If the error was due to the overload or high contention in the system, immediately retrying might actually make things worse. Imagine 100 transactions collide and abort due to the hotspot row. If all 100 will immediately retry, this could amplify the load and cause another round of conflicts. In such cases, it is often wise to implement an exponential backoff, that is, wait a bit before retrying or address the root cause. For example, too much concurrency on one item. Third is permanent errors. If a transaction is failing for a permanent reason, for example, violating a business rule or bug in a code, retries won't magically fix it. The application should detect the failure is not transient and avoid looping forever. For example, a transaction failed because it was violating a unique constraint. Retrying will fail each time until the data is changed. Retry when aborted is meant for transient failures like deadlock or timeouts, but not logical errors. Another one is external side effects. A big snag is if your transaction has side effects outside the database. Consider a transaction that, as a part of its work, sends an email or charges a credit card. Even if the database rollbacks a transaction, the email might have already sent or the charge have been made. Those side effects won't be rolled back by database. So if you retry the transaction, you might send the same email again or double charge the card. Now, this is the classic challenge to keep the transactions purely about database changes or otherwise coordinate the external actions carefully. One strategy is to perform external side effect after the commit has been made or use an outbox pattern to sync them. so that our bots don't accidentally trigger side effects. Another strategy is to make the side effects idempotent or checkpointed that doing twice will not make any harm. Okay, so let's move forward. Let's talk about ACID databases versus best effort databases. Let's talk about ACID compliant databases first. It provides transactions with atomicity and isolation plus consistency or durability. You get strong guarantees that simplifies reasoning. No partial commits and anomalies are minimized, especially if you are using a strict isolation level. For example, most SQL databases such as PostgreSQL, MySQL, Oracle, etc., and some modern distributed databases that preserves ACID properties. You can trust that if a transaction says it is committed, all of the changes are there. And if it is aborted, none of the changes are there. You rely on databases to prevent other transactions from seeing your uncommitted data. Now let's talk about best effort database. They do not fully guarantee multi-object atomicity or isolation. They might only guarantee the atomic operations on single records or might allow anomalies across multiple operations or during failures. They favor availability or partial tolerance over strict consistency. These systems might be labeled as eventual consistent or base. They require developers to write additional logic for integrity. For example, you might implement a manual compensation mechanism. If step 2 fails, then send a message to undo the step 1, etc. These databases are useful when you need to scale out and can tolerate a bit of inconsistency window or when the data can be corrected later. So here the conclusion is one of them is not better than the another, but it is a trade-off. ACID systems puts much safeguards while best effort systems prioritize other factors, but they ask you to handle edge cases. As a developer or an architect, you have to choose based on your requirements. If correctness or simplicity are a top priority, then go with the ACID ones. And if you need the last ounce of performance or 100% uptime across all the partitions, and can reconcile inconsistencies later, a looser approach might work. But you must be aware about atomicity or isolation gaps so that you don't introduce the critical bugs. So that's it for today's lecture. We have covered atomicity and isolation, single versus multi-object operations, little bit about atomicity, isolation, single object operations, multi-object transactions, what can go wrong without atomicity or isolation. Then we have handled failures and safe retries. Then we have talked about or discussed about ACID databases versus best effort systems. If you are still watching this video, then kindly please make sure you like this video, comment if you have any doubts, and please make sure you subscribe to my channel because it will motivate me to make more videos. And thank you so much for watching.